Hello students and welcome to lesson 6.05 honors teaching video on rate and collision theory. Again, to get to this point you are taking honors credit and have already completed the 605 regular assignment. First, just want to remind you of the Common Core standards that we are addressing with this lesson. And again, at this point you can pause the video if you'd like and read over those. You can also access them by going to course information when you're in the class and clicking on standards. Again, for 605, our objectives are to explain how various factors affect the rate of a chemical reaction and using the collision theory as a model for reaction rate. As I already mentioned, you do need to make sure you are understanding 605, the collision theory and factors affecting reaction rate. And if you need some help with those, please go back and review that lesson. You can also attend one of the open tutoring sessions to get some help. And make sure you're comfortable with that before you continue into the 605 honors. So with that said, let's go ahead and jump right into it here. In 605 honors, we're actually going to start putting some quantitative aspects to what we learned in the regular assignment. First, let's talk a little bit about rate, and we'll see how this transitions into the quantitative aspects of it. Rate, remember, is described as a change in concentration over a change in time. Now, we cannot really take each instant within that time frame and know exactly what the change in the concentration is. So what we're really taking is an average rate change over a given amount of time. Now we need to remember too that rate depends on the amount or concentration of the reactants present, which means then that from the moment the reaction starts, we're going to have a decrease in the concentration of the reactants. Therefore, the rate is also going to decrease as the concentrations decrease. So if you look at the diagram here on the bottom, we have hydrogen gas reacting with nitrogen gas to produce ammonia. And you can see that over here we have time 0, and as we're going along the reaction, which is our x-axis, that's time, you can see how the concentration of the hydrogen and nitrogen decrease and the concentration of the ammonia increases, which is what we would expect in that reaction. Now, because of this decrease in the reactants, that's in turn going to affect the reaction rate. So we're actually also going to have a decrease in the reaction rate. So that's why when we're talking about rate, we have to understand that we are looking at the average change in that rate over time. Because if you look at our graph here, the rate, or the change in the rate over time up here at the beginning, this is a quick drop off here. So we got a big change in concentration in a short amount of time. Whereas over here at the end of the graph, you can see it's more flat. So in the same amount of time, we do not have as much of a change. So the rate down here is definitely going to be less or different than the rate up here. Okay? So when we're looking at this example again, keep in mind the ratios. Right? We have 3 moles of hydrogen reacting with 1 mole of nitrogen to produce 2 moles of ammonia. So as you're looking at the graphs, you notice the nitrogen, because we're only using 1 mole at a time, this curve doesn't drop off as quickly as the hydrogen. It's relatively flat. Whereas the hydrogen, because we're using 3 moles at a time, it drops off quickly and goes to almost nothing pretty quick. And then again the ammonia, because we're producing 2 moles each time, that's going to have an increase as we're going across. Now at some point the concentrations of all 3 of these are going to level off, just like you see in the graph here. So if we continue this on for a long enough time, these graphs, of course I'm not drawing very well here, but will end up being perfectly flat. Once we get to that point, that is what we call equilibrium, and we'll talk about equilibrium in more detail in Module 7. Alright, so since we're really dealing with average rate when we're talking about change in concentration over change in time, we want to talk about, the actual calculating of average rate. And again, whenever you take the average of something, remember we're simply taking basically the total and dividing it by however many is involved. In other words, if you have 3 different assignment grades and you're asked to get the average of them, you would take your 3 grades, add them together, and then divide by 3 to get the average. Well, we're going to do the same thing when we talk about rate. We're going to take the final concentration, subtract the initial concentration, and then we divide that by the final time minus the initial time. Okay, so again, it's the change in concentration over the change in time. Simple as that. All right. Okay, so let's look at an example of how that would work. What is the average rate for this reaction over the first 4.32 times 10 to the 4th seconds? So what they're saying then is if we go from 0 to 4.32 times 10 to the 4th seconds, what is the average rate? Okay, so again, to get the average rate, we would take the final concentration and subtract the initial, and that would go on top. So the final concentration at that time is the 0.250 molar. The initial concentration was 1.000. For the time, we got 4.32 times 10 to the 4th seconds minus 0 seconds. So when we do our math, 0.25 minus 1, and then divide that by the 4.32 times 10 to the 4th, we get a negative 1.7 times 10 to the negative 5. Okay, and the units would be molar, right? This concentration per second, concentration per time. Now the negative sign, okay, does not mean we have a negative rate, okay? That just simply tells us the direction that the reaction is occurring. Okay, so normally we do not worry about writing the negative sign. We just worry about the number. So 1.7 times 10 to the negative 5. All the negative is telling us is the direction of the reaction. Kind of like with exothermic versus endothermic, the sign tells us the direction. Here's the same thing. The negative is telling us that we're losing the concentration, in this case of the H2O2, which is the peroxide. Okay, now just for practice, let's find out the average rate for the last half of this reaction. Alright, so now our final concentration is the 0.0625, and our initial is the 0.25. Okay, so let's use those values and see what our rate would be for the second half. So we got 0.0625 minus 0.25. And that would be over 8.64 times 10 to the 4th minus 4.32 times 10 to the fourth. Okay, so let's plug those in. All right, and for this one, again, we do end up with a negative value. All that tells us is that we're losing or lowering the concentration of the H2O2. And it's 4.3 times 10 to the negative 6 molar per second. Okay, so you can see, like we were talking about earlier, the rate for the first half of the reaction is faster than the rate for the second half of the reaction. And that is what we would expect, because as the concentration is decreasing, the rate will also slow down. And that's what we see here with the results that we get. So again, the negative, very important here, just tells us that the concentration is decreasing. In chemistry, we typically don't talk about just the average rate. What we like to look for is what's called the rate law. The rate law is simply an expression that shows how the rate of the reaction depends on the concentrations. And we kind of put everything together, if you will. Okay, right here's the formula for the rate law. Rate equals K times the concentration of A, that's what the square brackets mean, to the exponent or power of X times the concentration of B, also to the exponent or power of Y. Alright, so let's kind of break this apart, what this means. Of course, rate is just that. It's the rate that we're looking for that particular reaction. K is the rate law constant. And the rate law constant will change depending on the reaction we're talking about. A and B, as we mentioned, are the concentrations. And it's always going to be the initial concentrations in molarity for each of the chemicals involved. So if there's 3 reactants, then we'd have to include a C in that equation. If there's only 1, then we just get rid of the B. We just add and take away, the variables, if you will, as we need, depending on the reactants we have. Now, X and Y, those exponents are called orders. All right, and orders simply show us how each reactant's concentration affect the reaction rate. In other words, if the concentration is doubled, then how does that affect the reaction rate? Or if it's quadrupled, how does it affect the reaction rate? Things like that. And you'll see how this works here in a moment when we walk through an example together. All right. The value for X and Y can only be determined through experimenting. And then K we can then calculate. All right, so we're going to walk through this here in a moment with an example. Again, we are talking about initial concentrations, that third bullet point. I do want to kind of emphasize this. What we do is we take the initial concentrations and we start the reaction and we measure it from the beginning. It's much easier to just know our initial concentrations and solve from there than it is to try to determine the concentration at any given time during the reaction. So that's why we use the initial concentrations. So how would this work? Okay, well, again, this method is called initial rates. All right, so I already kind of touched on this a little bit. We're going to use this to determine the reaction's rate law. We always use the initial concentrations. Okay, so we're measuring the initial rate right after the reaction begins, that first initial rate of the reaction. We are going to do several trials because we're going to compare those different concentrations. And like I just mentioned, we're going to vary the concentration so that we get different results. And then we're going to compare each of them to determine the orders, the X and Y, and then we can finally plug it all into the formula to figure out the rate. Okay, so now let's look at an actual example, and it'll start making a little more sense here how we do these type of problems. All right, we're asked to determine the rate law, including the values of the orders and rate law constant for the following reaction. We've got Cl2 combining with CHCl3, yielding HCl plus CCl4. All right, now again, we take different trials of data. So in the first trial, we have 0.987 molar for the concentration of the Cl2, and we also have 0.987 for the CHCl3, and the rate, the initial rate of that reaction was 1.35 times 10 to the negative 11. Trial 2, we keep the Cl2 the same concentration, but we change the concentration of the CHCl3. Okay, so now if we compare trials 1 and trial 2, then we can look at how CHCl3 affects the rate because the Cl2 is held constant. It's kind of like, doing the scientific method. We hold one reactant constant, change the second reactant, and then see what happens to the rate. So, using your scientific method terms here, this would be our control variable between trials 1 and 2. This is our independent variable, and then over here the rate was the dependent variable. Now in trial 3, it's the CHCl3 that's held constant, and then we are changing the concentration of the Cl2. Okay, so again, we got now this is our control variable. The Cl2 is the one that we're changing, so that's our independent variable, and then the rate is going to again be our independent variable. Alright, so what we're going to do is, just like I mentioned, we're going to compare the rate law expressions for each of those trials and see what effect each concentration change has on the rate change. So let's look at how that would work. Okay, so let's do the first two trials. Alright, in the first trial, the rate was 1.35 times 10 to the negative 11. And remember that equals K times the two concentrations raised to the order. So the first one will raise to X, and then the second one we raise to Y. And again, we don't know X and Y yet. That's what we're trying to figure out right now. Okay. Now, since we're comparing them, we can set them up like a ratio or a proportion. So now the second trial, we have 6.75 times 10 to the negative 12 for the rate. Same K. The concentrations, now we got 0.987 still for the Cl2. And then for the second reactant, we got 0.494. And this time it is, again, raised to the Y. Now, remember the K is a constant, so the K on top is the same as the K on the bottom, so we can cancel that out. It's not going to change. The second expression is exactly the same on the bottom and top also, so we're going to cancel that one out. Okay, so on the right side, or on the left side, excuse me, we got 1.35 times 10 to the negative 11 divided by 6.75 times 10 to the negative 12. And on this side, that gives us a 2. And that is equal to the 0.987 to the Y over 0.494 also to Y. Okay. Now, to get this expression simplified, we could take the logarithm of this entire expression. All right, so go into math class here a little bit. So you take the log of that entire expression. Okay, so the log of 2 gives us 0.301. On this side, when we take the log of that, that gets the y by itself. Okay, so it's y times the logarithm of this entire expression. So if we take 0.987, kind of combining steps here, divided by 0.494, and then you take the log of that. So the log of that expression gets us 0.301 times x. So of course times y. So to get y by itself, of course we just divide both sides by the 0.301. So that tells us then that y, okay, so that tells us y equals 1. All right, so now we got to do the same thing between the second and the third, because in that one we're going to have the CHCl3 held constant. So if we do a comparison between those two, we got 6.75 times 10 to the negative 12 equals K. The concentration was 0.987, again to X, and then we multiply that by the 0.494 to Y. Set it up again as a proportion. Okay, on the left we've got 4.82 times 10 to the negative 12. And then we've got K. Okay, and this time it's the CL that's changing, so it's 0.834 X times 0.494 Y to the Y. Okay, so again, K is the same, so that's canceling out. The 0.494 expression is exactly the same, so that's canceling out. And now we're going to figure out the X there. So we got 6.75 times 10 to the negative 12 divided by 4.82 times 10 to the negative 12. And that's going to give us 1.4 equals, again, that entire expression, right, is 0.987 to the X over 0.834 to the X. Okay, and just like we did on the first one, to get X by itself, we would take the log of that entire expression. Alright, so log of 1.4 is going to give us 0.146. Okay, and then on the right side, take the log of that entire expression, 0.987 divided by 0.834. And on the right side, we got 0.0 0.73 times x. And again, we want x by itself, so we're going to divide both sides by 0.073. And you can see that that's going to give us x being 2. Okay, so just pause here for a moment. What that tells us then is that this reaction rate is first order when compared to the CHCl3, and it is second order when compared to the Cl2. Okay, now that we know the orders, what we do is we pick one of the 3 trials, and I'm going to pick trial 1. It doesn't really matter which one you use, and we're going to plug in all of the values we now have and solve for K. So if we're using the first trial, we've got 1.35 for the rate times 10 to the negative 11, and that is equal to K times the concentration of 0.987 to the second order, so it's to the second power. And then the second concentration is also 0.987, and that is to the first order. Okay, so on the left side we still have the 1.35 times 10 to the negative 11. On the right side we've got K, and then if we take 0.987 and square that and then multiply it by 0.987, we have K being multiplied by 0.962. Alright, so we divide both sides by that value to get K. So we got 1.35 times 10 to the negative 11 divided by 0.962. And that gives us a K value for 1.4 times 10 to the negative 11. So for our final answer to the problem, I'm going to write this over here on the left. We just put all these numbers into the original rate expression. So we say rate equals, K we just figured out is 1.4 times 10 to the negative 11. And we're going to multiply that by the concentration of Cl2 to the second power, and then multiply that by CHCl3 to the first power. And just like in math, we don't write the 1 there because it's already assumed to be a 1. And this here would be our rate law for this reaction. So now we know the rate law. We can take any concentration value, plug it into this formula, and figure out what the rate will be for the reaction in that given situation. And that is how we use initial rates to solve for rate laws. Alright, so that's how we do initial rate problems to determine the rate law. So now you can complete all the example and practice problems in the 605 Honors Lesson tab. If you're still needing some help, please attend the open tutoring sessions. We also offer a review sheet in the Resource Center. And once you feel comfortable with this material, you can then go ahead and take the quiz, which is found in the assessment section, or you can also access it through the gradebook section. I hope this was a helpful video for you, and we look forward to seeing you back here again soon. Thank you.